Hello, thanks for joining me. I am so excited to dig into circles with you. This is one of my favorite lessons, so I'm glad you're excited to be here. Just a quick note, if you haven't already found it, there's a note sheet that you can get from Schoology that has exactly what I'm showing on my screen. If you don't have the note sheet, that's fine. You can just grab a piece of paper and write it on your paper. I'm just going to remind you that you have a lovely geometer that allows you to draw beautiful circles, so this would be a great time to pull that out. I'm actually going to use it in a second here also, and you can recreate anything that's on my screen. You can pause the video as needed. And one more thing I just have to say at the beginning of this video is that on the back side of this note sheet, the second page of this note sheet, are all of the answers to everything we're about to discover. So if you want to be the person that knows the ending to the end of the movie before you watch the movie, then you can flip it over and look at it right now. Although the answers aren't there, they're pretty much set up for you. But I would encourage you to just not flip it over, not look at the second page, put it aside, and just join me and let's have some fun. If you like how class normally runs, I'm going to try to recreate the same experience where we get to play with math a little bit, where we pose a question and then we see, hey, what happens? So I hope you can sort of embrace that spirit and enjoy doing this with me, and we'll pretend that we're together. And I get to do this with you because, like I said, this is one of my favorite lessons. So, a quick review to get us ready for this. You have a vocabulary sheet that has a whole bunch of circle terms on it. You might need to grab that. Unless you're familiar with this term, so we want to draw and label triangle ABC inscribed in circle X. And then quadrilateral math inscribed in circle Q. So, keyword being inscribed. Go ahead, pause the video and try it, and then I will join you. So this is a fun fact about your geometer. If you don't know this, if you are using the same geometer as me, circle number 26 here says that it circumscribes 11 to 15. So we've got two words that are very similar, circumscribe and inscribe. Circumscribe sounds kind of like circumference, and that means goes around. Inscribed means inside. So if the triangle is inscribed in the circle, that's the same thing as saying the circle is circumscribed around the triangle. Triangle is inside the circle, circle is outside going around the triangle. Okay, we can reverse those, but that's for another day, another time. But this circle that circumscribes 11 to 15 means I can grab either 11, 12, 13, 14, or 15 and put it, and it will exactly go inside. So this right here would be an example of a triangle ABC that is inscribed in my circle. Okay? Now, just because I think it's fun, I'm going to give you one that is not circumscribed or not inscribed in my circle. So I'm going to have to use a smaller circle here. Let's use this circle, and if I were to draw a triangle that looks like this, so it doesn't have to be an equilateral triangle. Let's say I draw that triangle. Whoops. Let's pretend that I didn't just make that go too far, but let's say that this is my triangle ABC. That is an example of a triangle that is not inscribed in my circle. And the reason is, if you look at your definition of inscribed, maybe you already can say it. A polygon is inscribed in a circle if each vertex lies on the circle. So B and C would both have to be on the circle. It can't just be randomly in there. So that's a bad example. Please know that triangle ABC is equilateral but does not have to be. So I could have put point C down here, for instance, and drawn it so that my triangle ABC looks like this. Whoops, now you're seeing my lovely desk. And my purple triangle ABC is also inscribed in circle X. Okay, so you're probably getting the idea. Quadrilateral math inscribed in circle Q. And that would be, let me take a quadrilateral. So it doesn't have to be a square. It can be a square. But as long as you've got 4 lines connected. In fact, I've already got one right here. I'm going to change my letters, but I just want to show you that would be triangle quadrilateral ABCD inscribed in my circles. So change those letters to M, A, T, and H, and you've got a quadrilateral inscribed in your circle. And if you did the pentagon, that's great. I'm going to move on in the video, but you are welcome to try a pentagon or grab that one on your geometer, number 11, just for fun. Okay, so let's put some math with this. And I'm going to focus in here on number 4. So we've got a lovely triangle ABD. And notice this notation here. I'm giving you a D, and I want you to note that D is the center of the circle, and the reason I know that is because this notation right here, I read that as circle D, just like we used to say triangle, and we put letters after that. That reads as circle D. That tells you D is the center of the circle. So we know the measure of arc BC is 80 degrees. That is given. And we want to find measure of angle 1 and measure of angle 2. So pause the video, try it. Okay, awesome. So you figured out angle 1, if we're using our vocabulary, is a central angle, and that's the same as the arc, which is what we learned last week. So that's 80 degrees. And angle 2, well, that's going to make you think a little bit more because that is not a central angle. So that's interesting. My vertex is on my circle. That's an angle that's in my circle, but not a central angle. So how are we going to get that? Yeah, hopefully you use triangles because, well, triangles are the answer to everything, right? So how could I use triangles to help me out here? Well, I know this angle here is not numbered, but that angle is the supplement of angle 1. And if I just said that this was 80 degrees, then this is going to have to be 100 degrees. So maybe you did that. I see another way to do it, but I'm going to start with that. Now, what can you tell me about triangle ABD? Yeah, this is tricky. This is one of my favorite parts of circles, is that these triangles just like miraculously appear in my circles. But if I'm looking at this, it's not super obvious at first. BD and AD are special segments in my circle because they both come from the center. Yeah, that's right. They're both radii. And all radii in a circle are congruent to each other. So if those are congruent, what do we know about that triangle? You got it. It's an isosceles triangle. And if it's an isosceles triangle, then the base angles are congruent. And now everything in the world is falling into place. And angle 2 and angle A and angle B, we'll just call them that for now, have to be congruent to each other. So if they both add up to 80, since this is 100 degrees, and each one has to be 40 degrees. So that's 40, and that's 40. I'm running out of room, but those are the angles inside of my triangle there. So maybe you could figure out a different way to get that. If you're not seeing that first, let's think about what this angle 1 is in terms of my triangle. So try to ignore the circle, just look at the triangle. Angle 1 is outside the triangle. We have a special name for that. We call it the exterior angle, and there's an exterior angle theorem from triangles. Maybe you want to pause and look that up. See if you can make sense of that. Okay, cool. So we figured out that angle 2 is 40 degrees. Okay, so I'm going to pull this away, and I've got 3 more problems there that I'd like you to try, or you can follow along if you can't read them on this screen, on your note sheet, and go ahead and give them a try. Cool, so hopefully you were able to get that e.g. angle 1 is 24 degrees and angle 2 is 12 degrees. I use the exact same reasoning as the last one. That's interesting. I'm noticing a pattern here. I don't know if you are. 24 and 12, 80 and 40. Let's see what happens when we reverse it. So if angle 2 is 36 degrees and I still have an isosceles triangle here, then this is 36 and this is 36. 36 plus 36 is 72. Subtract from 180. This is 108. Or wait, this is the exterior angle. Has to be the sum of the 2 interior angles. So angle 1 equals 72 degrees and arc BC equals 72 degrees. And angle 2 here is 15, so angle 1 ended up being 30 degrees, and arc EG also was 30 degrees. And now, because you guys are very observant people, we all are, by human nature, we naturally want to make patterns and make sense of the world. You are all seeing this fabulous relationship, and the relationship you're seeing is that this angle, which we haven't yet named, but this angle that we have here, this is just like in class, guys. I'm just trying to find a color that I want to use, so give me a second to find a color. Blue looks fantastic. This angle right here that seems to have its vertex on the circle, and I'm also always calling it angle 2, but I don't always have to. that angle, if I look at that in relationship to the arc, because we said last week the central angle was equal to the arc. Remember, this 80 was equal to that 80 degrees. And this 72 degrees is equal to this 72 degrees. Now what we're seeing is that this angle here is 30 or 36, but the arc is 72. Or let's go back to this one. This arc here was 80 degrees, but then we ended up with that angle was 40 degrees. So we see this distinct relationship that the angle ends up being half the arc. Angle is half the arc. So pause if you need to and just make sure you agree with that. And then I'd encourage you to do two things. One would be, by all means, if you are interested, that we could totally turn this into a 2-column proof. If that's your style and you want to kind of work it out. The angle 2, we could generalize that, and then we just started with a random arc measure. So just refer to that as arc BC instead of actually putting a number there, and you could generalize it. Or you could just try some more numerical examples. Okay, if you're interested, there's a proof in your book. Look in section 12.3, and you can also follow along with that. Two other options. There's some cool activities in LinkedIn Schoology that take you to GeoGebra activities where you can play and explore dynamically and see how that angle changes as the arc changes. And then, because I am super prepared, I brought my visual with me. So join me and I'm going to show you a quick little fantastic visual. By the way, we're going to refer to this angle to throw a new vocabulary at you, where the vertex is on the circle, as an inscribed angle. Yeah, get it? Remember we talked about these inscribed polygons? They just have 3 inscribed angles or more, depending on how many angles I have. Cool. Okay, so let's go and look at this very fabulous circle. I apologize for my moving my screen and things going crooked and wacky. Okay, so I want you to look at this circle. I'm going to see a little bit of my desk here. It's worth it, don't worry. I promise you, this is good. So we've got, my document count almost isn't tall enough. Okay, I've got this lovely circle that I've got drawn here, and I've got a central angle. Just trust me, D is the center of this circle. Cool? Okay, so I've got this central angle I essentially wanted to cut out. So I cut it out, and here it is. This is the measure of that central angle. However big it is, I've got it. It's in my hand right now. Now, I want to draw an inscribed angle, so I'm going to have to use a different color here. Bear with me. Inscribed angle, and that's because I already have ADC. My central angle is blue, so I'm going to make it red this time. So I'm going to draw an inscribed angle. That means I'm going to pick any point on the circle. I just happen to pick B. We okay with that? Okay, thanks for going with it. So I'm going to draw an inscribed angle from A to B to the same points. So we've got a special name for this arc. We call this the intercepted arc. It's the part of the circle, interception. Think in football, an interception is where the other team intercepts a throw. They catch the ball, they take over, they cut off the other team from getting it. So we're intercepting our circle. We're cutting off this part of the circle. So this is my intercepted arc. And we said this angle, this inscribed angle, should be 1/2 of my intercepted arc, or 1/2 of this angle, since this central angle is equal to this arc. So here's what I'm going to do. I'm going to take this angle. I'm going to fold it in half. Exactly. You ready for this? You're not ready for it, are you? Nope, you're not ready for it. You ready? How do you feel about that? Okay, please tell me that's the coolest thing that you've seen all week. That's awesome. Okay. So you could try that on your own if you want to. Just try any angle. And actually, before I move this, because I know you're not done yet. I know you want to see more. You're not convinced. Let's just pick another point. So you're not convinced. Let's pick another point. I'm going to call it E. And I'm going to put it somewhere on my circle. Where do you want me to put it? Yeah, you want me to put it over here? Okay, cool. So I'll put it right here. Remember, if you wanted to put it somewhere else, you can try it on your own. There we go. So I'm going to make another angle here. I'm not liking this marker. And then I'm going to draw from here over to here. So remember, I'm using these same 2 points because I want to use the same arc. So that's okay that it overlaps here. It's fine. I'm just focusing on this arc right here. And the intercepted arc is still this arc stretching from A all the way to C. I'm still got that same arc. So I'm going to take that arc measure, which is the same as the central angle measure. I'm going to fold it in half. Ready for it? Boom. Fantastic. That is the most satisfactory thing that I've seen all day. Okay, thanks for joining me for that fabulous visual. I know you loved it. So we now have established, now would be a totally appropriate time to flip that paper over, but before you look at the back side, don't look at the whole thing, just look at the top. Yes, you heard me. Just look at the very top section, and we are going to fill that out together. Or you can go ahead, actually, while I shuffle papers here, and make it continue. So I'm going to, there I go, telling you not to look at it, and then I show you it. Okay, I hope you didn't look that quick. So we've got, get this somewhat centered and straight so you can read it. Okay, I think you can read that. Cool. So we've got inscribed angles. Inscribed angle. The measure of an inscribed angle is, in words, let's go ahead and write it. I'll write it with you. If you don't have this on your paper, if you're not printing that out, go ahead and pause and make sure you're getting this whole thing. You could draw a little picture and make sure you're putting titles with this so you're keeping your notes organized. Is half one-half the measure of its intercepted arc. That's what I said in words before. And then we have a lovely picture here, so I think we should go ahead and make an equation, because we can say this in an equation form. And that means that measure of angle B means equals 1/2 the measure, remember we put that little m just to refer to the measure of arc AC. And I like to give myself a second equation here, because there's an implied second equation. So far we said the angle is half the arc. Let's put an example here. I don't always like an example. Maybe you don't want to do this in your notes, or maybe you just do it in pencil so you can erase it. I'm going to go ahead and do it up here, but I'll grab a different color so it's not looking like it's permanent. So if I know that this arc is, let's say, I don't know, let's say that that's a 100-degree arc, then the measure of the angle would be half of that, so that would be 50 degrees. It's as easy as that. Now, if we know the angle is 50 degrees, then how would we find the arc? Yeah, we would just double it. So we could actually write that down, that 2 times the measure of the angle is equal to the measure of the arc. And I meant to say angle B, I apologize for that. 2 times the measure of angle B is equal to the measure of the arc. So it gives you a way to get both of them. If you know the arc, then you're going to double it to, if you know the angle, you're going to double it to get the arc. If you know the arc, you're going to cut it in half to get the angle. Okay, so this might have you thinking, hopefully this is having you thinking about a couple other things. And you may remember a word, I haven't used it a ton, called a corollary. And that just refers to a theorem that's really closely related to the theorem that we just talked about and have essentially proven. We sort of did it experimentally this time. Maybe you actually wrote a 2-column proof. So I want to look at a couple corollaries of this theorem. And I think we already looked at one, so I'm going to go back to this lovely picture. Remember these angles? We said that angle E and angle B, and oh yeah, there could be other angles, right? I just stopped at 2, but we said that those were each half of the arc. So an indirect conclusion there is that these angles actually had to be equal to each other, because they were both equal to half of arc AC. So what happens is when we have a couple angles that have the same intercepted arc, they're always going to be congruent to each other. So let's just look at this first one here. 2 inscribed angles that intercept the same arc are congruent to each other. And I've already got that actually drawn in the picture here. So I'm going to put a little statement down here that angle A is congruent to angle B, is my specific example that I'm using. Okay, and why is that? Again, because they're both half of the arc. So angle A is half of arc, let's add some letters here, is half of arc CD. That's the arc that's inside of it. Sometimes I like to cover that up if that's hard for you to see. Cover up the sides there. I can actually get, sorry, that noise was my desk drawer. So I was getting note cards out here. So sometimes I like to do this and cover up the rest of the circle. So that arc is the arc that's inside my angle there. And then if I go to this other angle, well, guess what? It's the same arc that's inside of that. So therefore, they have to be congruent to each other. Okay, two other corollaries, but let's take a look at an example I think will help us establish these. So I've got a circle here. Let's look at the circle on the left first, circle A. If you'll notice that circle A, I now know something about point A. Yep, point A is the exact center of the circle. So my question is, what happens if I have an inscribed angle whose intercepted arc is arc B? I can't call it BC. Why can't I call it arc BC? As a review from last week, why is that bad notation? Arc BC would be what kind of an arc? This looks like a minor arc, but that would have to be less than 180 degrees. If BC is a diameter, then the arc that goes from B to C is a semicircle, and I name that with how many letters? Yep, you got it. You name it with 3 letters. So BDC could be the arc name if I put a point somewhere over here. Now let's put a point somewhere over here just for fun. And let's call that E. And then let's actually make an angle here. An inscribed angle from B to E to C. And I want you to tell me, what can you tell me about angle E? Inscribed angle. Let's use our inscribed angle theorem. We just established an inscribed angle is half the arc, so I need the arc. Again, the arc's inside of that angle. So if I cover up that angle, I would be cutting off this arc from here all the way to there, which is how many degrees? Yeah, that's 180 degrees. So if I cut off this 180 degree arc, whoops, sorry, document camera. If I cut off that 180 degree arc, I can't get that straight. Then, there we go. If I cut off that 180 degree arc, then I would be cutting that in half, and what do I get? Yep, I get 90 degrees. Does that make sense? What happens if I put that point somewhere else? Yeah, I could put that anywhere I want. I could have put E over here, put it down here, and as long as I'm connecting to the end points of my diameter, I'm going to have a 180 degree arc, and therefore my angle is going to be a 90 degree angle. So that's kind of a special case. Again, it's really just my inscribed angle, but it's sort of a special case that we like to talk about. So that's what we're going to call corollary 2. And I don't really care about the numbers here. Okay, I just care about the concept. So corollary 2 tells me that an angle inscribed in a semicircle is always going to be a right angle. And hopefully that makes sense now that we kind of explored it, and there we go. So angle C is a right angle, and of course you know that that means it's 90 degrees. Okay, the next one is my favorite. Please, please, please don't look. Please don't be tempted to just jump to conclusions. Stick with me. This one is cool. Okay, so we're back to our inscribed quadrilateral. Remember that from the beginning of the lesson? Of course you do. Okay, so let's start with, I need to give you a random angle measure. So we are going to start with numbers here. So let's start with angle D. I'm going to tell you is 100 degrees. That seems pretty reasonable, right? Can you go with that? Yeah, okay, cool, thanks. So if that's 100 degrees, then I would like to know what the measure of, without any guessing, what the measure of angle B is. Measure of angle B. So you can take a guess. You can kind of just make a conjecture. But then let's work it out. Okay, so this is good sort of prep for what kind of reasoning you have to do to solve problems involving these theorems. So I'm going to say that whenever you know an angle, you know an arc, and whenever you know an arc, you can get an angle. So right now I know the measure of angle ADC, which means that if I follow that out, and sometimes I like to kind of highlight, so let's do that. That means that the arc inside of there, that means all of this, is the arc that's inside my angle, my inscribed angle, and therefore the arc, we said, is how much of the angle? 2 times the angle. Yeah, we're going backwards here. So that means the arc all the way from A to C is 200 degrees. Okay, I could write that as this. Measure of arc ABC, because that is a major arc. It's 200 degrees. Oops. Okay, so what did that do? Well, I don't know. Sometimes I just find things because I can, right? And then sometimes it leads me to other things. So let's just see what that led me to. Well, if I go over here, then I've got the rest of the circle. Wow, that marker's pretty dark. But let's go with it. The rest of the circle from A to C, yeah, that's the minor arc, has to be the rest of 360 degrees. So 360 minus 200 is 160 degrees. So that's the measure of arc AC. Is 160 degrees. Why do I care about that? Well, maybe I don't care, but maybe I do care because it looks like angle B is an inscribed angle that has, let's see if this works, has arc AC as its intercepted arc. So if I actually trace this angle right here, okay, or I said you can cover it up, so if you haven't already gotten note cards, come on, get with the program, or rip a piece of paper, whatever you need to do, sticky notes, those work. So you can see that 160 degree angle is the arc, or sorry, that 160 degree arc is the arc for the intercepted arc of angle B, which means angle B inscribed angle has to be half that arc, which is, yep, 80 degrees. Okay, come on, observant people, what are you observing? That number special in math? They're not congruent, that's my first thought. But I could have told you at the beginning, because this one's obtuse and that one's acute. But you gotta be noticing, come on, you gotta be noticing that together those add up to 180 degrees. And let's be honest, that's not the first time we've seen 180 degrees in this class, right? So then I'm asking myself, does that always work? So if you want to play, pause the video and you're welcome to play. Try a different number. I just randomly decided 100 degrees. Or what could we do to make this even more fun? You got it. Let's go ahead and do it together. So what I'm going to do is I'm going to make my angle into a variable. Instead of calling this x, 100 degrees, let's call that x. And if that's x, then this was 200 degrees, but we're really going to call that 2x, right? And then if that's 2x, well, let's think back to how we got this 160 degrees. That was the rest of the circle, 360 minus 200, so let's call that 360 minus 2x. And then how did we get the 80 degrees? Well, the 80 degrees was really half of this, so I need 1/2 of 360 minus 2x. That was just my specific number. So 1/2 of 360 minus 2x, well, 1/2 of 360 is 180, and 1/2 of 2x, we can distribute that, is x. Isn't that another way of saying supplement? 180 minus x. So the measure of angle B is what I'm writing right there. 180 minus x, which is angle D. So hopefully you're convinced, but like I said, please convince yourself, however long that may take. And then when you're ready, join me on the note sheet and we will uncover the third corollary for inscribed angles, which is the inscribed quadrilateral. Opposite angles in an inscribed quadrilateral in a circle are always supplementary to each other. They're supposed to be just two p's. So if you want to give yourself an example, sometimes I like to put that into equations. It's hard to kind of draw on your picture because they're not congruent to each other. But you should have a little room here. You could put measure of angle A plus measure of angle C equals 180. I know we didn't look at the other pair in our particular case, but you certainly could do that. Cool? I know what you're wondering now. You're wondering what quadrilaterals can and cannot be inscribed in a circle. Sometimes, always, never. That'd be fun to think about. Okay, I promise you I'm almost done. This video is 29 minutes at the moment, so it's going to be about 35 minutes when we finish this off. Now would be a great time if you haven't already done so. Get up, stretch. I'm going to do the same thing. Okay, ready for some more. We're going to do 2 examples is what we're going to do, because I want to make sure that you can apply this, and it's fun to talk about why things are true, but you do need to be able to kind of put this into practice. So just so you don't get frustrated, let's just go ahead and walk through two of these together, of course, we're going to start with my favorite, the quadrilateral, which should be pretty easy enough. We just talked about that. So I also want you to see some different notation that sometimes textbooks use, sometimes you'll see, sometimes I'll use, and I don't want you to get confused by it. In particular, the notation here is they're using lowercase letters to refer to arc measures instead of putting letters here for all the vertices. So we're going to assume that if there's an A here, or any letter, that goes from the point that it's closest to. Whoops. Sorry about that. That goes from the point that it's closest to the next point. So that's going to go from here, whoops, all the way over to there. So that's A, and then B is going to be the next one. B is going to go from here over to there. What it is. Okay. So the first part of this, we don't have to go in order, A, B, C, D. So I'm going to go ahead and steal your thunder. Hopefully you already did it. You were just dying to do this, right? That's 100, so this is 80 degrees. How convenient. That's the same numbers I use. This is 96 degrees. I don't know. That's a lot of math for right now. But I'm going to do it. 180 minus 96 is what? 84? 84, I think. Check my math. Hopefully that's okay. Okay, so that's what we said about quadrilaterals. Opposite angles are supplementary. Those are supplementary. Those are supplementary. Cool. We didn't say anything about arcs. So what are we going to do for arcs? Well, we're going to remember that an inscribed quadrilateral is really just 4 inscribed angles. So, hey, we can do that, right? 4 inscribed angles. So let's see what happens if I go ahead and draw, because sometimes that helps me to visualize things. I was having fun with the purple. Let's go ahead and use the purple. So if I draw, you know what, I think this note card might work really well as my ruler because it's smaller. If I draw, so I want to kind of extend things. This is just like a way that I have of visualizing this, so this may help. May help you, may not. I'm having trouble fitting it under my document camera, but you get the idea. Trying to extend that, trying to extend this. Okay. That was not exactly what I planned to do, but you get the idea. So I'm trying to look at this arc here is the arc that I know, because this angle is 84 degrees, or I could have picked any one, right? Let's be honest, I just picked one. If this is 84 degrees, then 84 times 2 is what, 168? That means that this entire arc that covers A and B both is 168 degrees. Cool. But do I know how much A and B are? They certainly don't look equal, and I don't think I can assume that. So how am I going to find the measure of each? Well, just for fun, let's go ahead and try a different one. Okay, what if I hadn't drawn that one first? What if I had instead decided to do this? What if I had decided to look at this angle and the arc inside of there? Yeah, it's okay. You can cover it up. I know it helps, doesn't it? Thanks for agreeing with me. Cool, so that arc is twice 100, so that's 200 degrees. So that means 200 degrees has to go from here all the way around. This gets a little complicated, doesn't it? That's my 200 degrees, that green arc. So how's that help? Well, think about it. If that's 200 degrees, and we know this part's 99 right here, well, 200 minus 99 is just over that, which is 101, and the remaining part of that is A. So I actually just figured out that A is 101 degrees. See how I got that? 101 plus 99 equals 200. That just kind of happened, didn't it? So quadrilaterals are real weird because we always end up with 2 arcs. But now look what happens. If I uncover that and go back to this 168 degrees, yep, 168 degrees, which was this arc, the sum of A and B, I just figured out A is 101. So that means 168 minus 101. I know I should be able to do that in my head. That's 60... Not 69, 67. Wow. Okay, 67 degrees. B is 67 degrees. Make sense? Cool. That's your challenge. It's about as hard as it can get right now. Don't worry, next week we're going to add to this. Things are going to get more wacky and weird and fun. Okay, one more here, and then we will call it a day. Thanks for sticking with me. So, on a positive note, this is shorter than class. It's not going to be 48 minutes, promise. Okay, example 2 here. So, I wanted to give you an example of a more complicated picture because, oh yeah, you're going to see them. So, what happens when things get crazy and I start adding lines? Well, remember what I said a little bit ago. I said angles can tell you arcs and arcs can tell you angles, and you're going to do exactly that. Whenever you see something that tells you something else, you're going to put it in your picture. I need to make one quick note here. I apologize. X and Y are not necessarily congruent to each other. I was trying to show you that we're referring to the angle from here to here, because people get confused and they start to look at this curve, the circle, and think that that's what the X means. So that's this angle here, and if it makes you feel better, let's put 2 arcs here, so we know that that's a different one, and that's going from here to there. Okay? Okay, cool. So what do I know? Back to that question. Well, I know this is 140 degrees. That's the arc from here to here. So that arc's going to tell me an angle. It could tell me a central angle, but I don't have the central angle drawn there. So if you want to, you can draw it in. Or we can draw in the inscribed angle. Anybody want to look at that? Cool. That inscribed angle is going to be how much of the arc? Yep, 70 degrees. So that's going to be half of the arc. So that's 70. Now you're looking at triangles, right? I told you triangles never go away. 70 and 60 is 130. Subtract that from 180, and there we go. We got 50 degrees right here. So why do I care about that? Because angles tell me arcs. Arcs tell me angles. But now I have an inscribed angle here. So the inscribed angle is telling me an arc somewhere on that circle. Let's find it. So let's follow this out. And if I follow that out, then the angle the arc inside of that angle. Are you seeing it? There you go. Now you're seeing it. That is going to be twice the angle. So the angle's 50 degrees. Therefore, this arc is 100 degrees. Where's that? That's going from here all the way to here. And now by process of elimination, angles, arcs add up to 360 degrees in a circle. So now we've got 100, 140. Come on, you do the math. What is that, 240? Subtract from 360, I'm getting 120 degrees. Anybody agreeing with me? Cool, for that arc there. But I didn't ask you for the arc, so what's that going to do? I asked you for the angles. X and Y are angles. What kind of angles are X and Y? Yeah, that was a great answer. They're angles that we haven't looked at yet. Or have we? The vertex is on the circle. So what did we look at already where a vertex is on the circle? Well, that's the topic of the day, inscribed angles, folks. But this is a weird inscribed angle. It's a different inscribed angle, and if you're getting confused by it, I totally understand why. Everybody gets confused by it, because it doesn't go nicely across my circle, like this inscribed angle here, or this inscribed angle here, where we have 2 chords. Okay, now I'm using big words. Chords, segments inside my circle, usually form an inscribed angle. So up here, let's go back up here, we have 2 chords forming this inscribed angle. What do we have here? If we look at just this angle X, we have a chord, and then we have a line that's intersecting my circle just once, and we know what that's called. That's called a tangent. So that's still an inscribed angle. An inscribed angle is an angle where your vertex is on the circle. So we've got a chord and a tangent, and we're still going to say that's half of the arc. So big idea, this angle is 60 degrees, and then we can come over here, the 100, this is going to be 50 degrees. So X was 60 degrees, and Y was 50, in case you couldn't read my sloppy writing there. But more importantly, I want you to know that that's not a new vocabulary. It's still an inscribed angle, but we're going to draw it. If you don't already have this note sheet, you're going to draw this, and the rest of us are going to write this, because we do need to have this as an example in our notes. It will confuse you if you don't write this down. So, last thing I'm going to make you write down, I promise we will wrap it up at 40 minutes. Thanks for sticking with me. The measure and angle formed by a tangent and a chord is half its intercepted arc. And I know I sound like a robot. That's the same thing that I put up above. That's because it's the same kind of angle. So, I've got 2 examples there for you. And the reason is that I want you to see 2 different ways this could look. So the measure of angle C is 1/2 the measure of arc BC in the first one. And notice this one I named arc BC as a minor arc, 2 letters. And in this one, measure of angle C, we can use 3 letters if we want, or since that's the only angle C drawn in the picture. So if you want to call this AC. And the only reason I would do that is that this line could be extended, right? That tangent could keep going. So if I call that angle ACB, it's a little clearer that I'm referring to that angle right there, is still 1/2 of the arc inside of it. So I'm going with this angle, or sorry, that arc. But now I would have to use 3 letters to name that arc. So I could call that arc something, something, something. D is the middle point, and I've got CDB or BDC. We'll do that to go alphabetical between the endpoints. So that's two ways that it could look. Okay? It's just a little weird because the vertex of the angle is actually a point on the arc. It's one of the endpoints of the arc. So that one's going to bug you a little bit, but I wanted to give you something to challenge your thinking. I hope you enjoyed this lesson as much as I did. Like I said, I really, really, really do love angles and circles, and there's more fun stuff coming, but this is enough fun stuff for you to work with right now. So I'm going to stop talking. I'm going to give you one more thing to think about, and I promise I'll be done. I just want to leave you with one thought, and that thought is, what happens if I have exactly the case we're just talking about, so a tangent line, but my chord is the diameter of the circle. Do we all agree that a chord is just a diameter is a special chord? So if I go back to, can I use this picture? Oh, that's going to be confusing. Let's just draw another one real quick. If I have a circle, oops, we'll pretend I didn't just move everything. And I've got a diameter, so let's say that goes right to the middle of the circle. This is circle A, and then I have a tangent at one of the endpoints of the diameter. So let's say I want to find the measure of angle ABC. What happens there? So that's the same as what I was just talking about here. That's another example of what we've got drawn here. I've got an inscribed angle with a tangent and a chord. In this case, my chord is a diameter. And therefore, this should be half the arc. So what happens if I look at this arc? That arc, since I've got that arc is going from endpoint to endpoint of my diameter, yeah, it's half the circle. So that's a 180 degree arc. If that's a 180 degree arc, then my angle is a 90-degree angle, and we put a box there, and we say that a tangent will always be perpendicular to a radius or a diameter. That's pretty cool, isn't it? Okay, that's a fun thought to leave you with. I really am going to stop talking now. Thank you so much for watching, and I hope you have fun working with angles and circles.